In this video, we're going to come up with the tangent plane for a given surface. So this is our surface. That's our surface at this given point, this blue dots here. So our job is to come up with the equation of the tangent plane that just touches this point here. So search this up in Google, type in Geogebra and make sure it's in 3D. Punch in our surface and punch in our point. So that will then give us this thing here. That will then give us this thing here. So currently our surface is this. This is our surface here. This is our surface. So the function diagram can be represented by this. But when I take away z from both sides, this will then be equal to 0, giving us this. So currently this is our function diagram for this. I do have the right to visualize this exact same thing by visualizing it like this. So this diagram can represent this, because we input, if you look at this thing here, we input 3 variables, x, y and z. So I'm playing about with x, y and z. I can do whatever I want over here, and then it will spit out, let's imagine it spits out an f. Well, here in our case it spits out an f where the value of f is precisely 0. So given this, I do have the right to visualize it like this, or I can visualize it like this, where it spits out a specific value of 0. So we are just really looking at the exact same thing, but we are visualizing it in a different perspective. Meaning this thing here, I can visualize it like this, where I can play about with x, y and z. I can represent it however I want. I can represent it however I want, x, y and z, and then it spits out a constant c. It spits out, in our case, it spits out a value of 0. So I'm visualizing it in this form here, because the reason why I'm doing this is because when it equals a constant, later on when you differentiate this side, it equals 0. When you differentiate this side, it equals something. But by knowing that when this equals 0, it gives us some insight into what's happening over here. I will explain later on. But so we are currently here at the moment, which can be represented by this function diagram. I can use a new variable called time, let's just imagine it as time, to drive the particle around. So this is us using our parametric equations technique. We use this thing called time to drive the particle around. So what that means is like this. What that means is this. I can use this variable called t to drive the particle around the surface. So this particle can move however I want it to move. I can use this t to drive the particle, and it will always stay on that surface. So hang on, going back to here. So we are currently here. I can use this variable t to drive the particle around. So now I can differentiate it. So by using implicit differentiation, which I'm not expecting you to know this by now. So when you use implicit differentiation, it's given by this, and then when you get to this stage, you can imagine this whole thing as being one vector, dot it with another vector. And we've done this before, and I'm expecting you to know this by now. This thing here is we're just going to assign a new name for it. We're going to call it Grad F, and then this is our velocity vector. This is our velocity vector. So what that means is, well, here when you take the dot product of 2 vectors and it equals 0, you will immediately know that they're at 90 degrees to each other. Remember this thing? When the angle is at 90 degrees, when it's at 90 degrees, then cos will be 0, meaning the dot product equals 0. But the point I'm trying to make here is that by visualizing it like this, when you differentiate this, it gives you 0. This thing here will then give you this thing here, but here you've got one vector and another vector. You know this equals 0, so which implies that these 2 vectors are at 90 degrees to each other by doing this. And remember, I've done lots of explanations on this. So these 3 steps I'm expecting you to know. So what that means is this, hang on. You've got this thing here called time, which drives a particle around. So let's just say our particle is moving around like this. Let's just say it moves around like this. So so when you differentiate it, you will get your velocity vector, and your velocity vector is always in the direction of the movements of your path. And then this grad f will always be at 90 degrees. So grad f will always be at 90 degrees to your velocity vector. So the particle is moving around like this. Let's say the particle is here. When you differentiate the position vector, it will give you your velocity vector, and your velocity vector is always in the direction of your path. But then, but when you compute grad f is always at 90 degrees. I don't know which direction, but it will always be at 90 degrees. So that's what this thing is saying down here. Hang on. That's what this thing is saying down here. So now so in the next video I will explain how we can compute the tangent plane. So we are currently here. No, actually, let's just do it. So this is our surface here, and the first step is to compute grad f. So grad f is when you take the partial derivative of this whole thing here with respect to x. So grad f is with respect to x. So when you differentiate this with respect to x, that will then give you this. So that's your I component, and for the j, grad f with respect to y, which would then be this thing here, j hat, and then with respect to z, which would be -1, so that's just -1k. So grad f equals this, but we want to evaluate grad f at a specific point of 1, 0, 0. So let's evaluate grad f at that point, which would then give us, well, you would put this into the x, this whole thing here would, well, put 0 into the y, this whole thing here will then become this. So grad f, so punch this into Geogebra, this is our grad f. Our grad f is this, hang on, grad f is this, is 2, 0, -1. So so define a vector. So this is our vector here, and then this is our blue point here. And then type this in, vector, and then your starting position, and then your end position. So this is our vector b here. So this is grad f here. This is our grad f. Yeah, so this is our grad f. So we need to draw the we need to somehow come up with the equation for the tangent plane. Now that we know grad f, remember the plane is always at 90 degrees to grad f. So hang on. So going back to here, so we know grad f is this. To describe the plane, well, what is this red vector here? This red vector here is given by this, because well, I'm expecting you to know this by now. The equation of a plane, if you can't remember, look it up. But the red vector is given by this, and the grad f is given by this. And then you demand that the two vectors to be at 90 degrees to each other, meaning the dot product must be equal to 0. So now compute the dot product. This times this will then give you this. This times this will be 0. This times this will be negative z equals 0. So therefore the equation of our plane is given by this. So if you punch this into Geogebra, that's our surface there. So that's our plane there. So now this is our plane here. You can see that our plane is at 90 degrees to grad f. So that's our tangent plane. Okay.